Okay, the purpose of this video is to look at something called significant figures and looking at measurement and how accurate you have to be. And then at the end we'll look at adding, multiplying, dividing, and subtracting with significant figures, which is different in sciences than it would be in math. Similar kind of thing, but in science we look at precision a little bit more. For example, in precision, take a look at those 5 statements. I'll be there Wednesday morning, Wednesday more early, 9:30ish, precisely at 9:30. All of these have a different type of precision, and in science we want to get as much precision as we can. But if we are using a number that doesn't have much precision, we can't go more accurate than that. So if somebody says they'll be there Wednesday, we can't tell our buddy, yeah, they'll be here Wednesday at noon, because we don't know. We know that they'll be here sometime Wednesday. So precision is an important thing in science. So when you measure anything, it always comes with some kind of an estimation and a certain degree of accuracy. So if I say measure a house and the square footage is 1156 square meters. When I look at this number, these 3 digits at the start would be ones that would be exact. Like they're exact. I know it's at least 1,150, but then I'm sort of not sure on that last number. It's close to 6. It could be a little high, a little bit low, but that last digit is one that's always estimated. So I have some exact ones and I have an estimated one. For example, when we're measuring volume, here I've got a volume thing and say I want to measure a little bit of that liquid that's in there. When you measure any kind of liquid, you do it with the meniscus, and the meniscus is that bottom part. See how it sort of goes up on the edges? When we measure a liquid, we don't measure at the top here, we measure right down at the bottom there. So I'm not exactly sure what that number would be. So it's 10, 11, 12, 13, 14. I don't think it's quite 15. I know it's for sure 14, so I'm calling 14 as my exact. And then I'll put a decimal, and that last number, it's not quite 15. Maybe I'll put a 9 there. So these 2 numbers here are my exact numbers. And the last number, this decimal place, is my approximation or my estimate. Okay. Some graduated cylinders measure even to 2 decimal places, or probably beyond that. And some of them can't even measure to 1 decimal place. They would measure just to this digit here, the ones digit. So you need to be able to look at your device and be able to measure accordingly. So that's volume. How about measuring distance? Here I've got a ruler. It's funny, they call this the lucky ruler because there's no number 13 on it. Anyway, if I wanted to measure the side of this triangle, I'll just put the triangle, try and get it sort of perfectly right on the end there. And then I'll take a look over here and see how far that is. Again, I know it's at least 4 point. And then that next number, it's sort of hard to read there. I'm thinking, well, it's not 5, it's not 4. I think it's just over 3. So it's 4.3, and then I have to ballpark it, maybe 1. And you may not be able to read that real well, but again, the point is I have some exact numbers. I know that it's exact, at least 4.3, and then this number here is the one that I'm guessing on, or I'm making an approximation on. Okay, so that is distance. Now we also have to weigh things, and fortunately when we have scales, the digital readouts on the scale tell you what the number is, and there's no real ballparking. However, that last number on the scale is an estimate. When you go and weigh something, you'll often see that last number fluctuates a little bit. And so if I have, when I weigh it, and it comes out to 4.382, then these numbers are the exact numbers, and this last one here is an approximation number. Okay, so we weighing anything or measuring anything, typically what we want are all the exact numbers and one estimate. Also, when you are weighing things, typically you want to get, or measuring anything, you want to get as much accuracy as possible, because then if you have to add, subtract, multiply, and divide that number, you've got good accuracy. Going back to that first thing of they're going to arrive Wednesday or Wednesday at 9:30, the person to be happy or to be not having to worry all day is the one who knows exactly when that person's coming. If you're not quite sure, then that's I guess it's not as accurate. Anyway, point is you want to maintain as much accuracy as possible. Now, we've just been talking all about measuring things, but sometimes we count things. When we measure things, there's always exact and one rounding. If we're counting, this is all an exact number. And when we talk about significant figures, in this one here, it'll have unlimited significant figures because it's a counting thing. There's an exactly, like in this in here, there's exactly 7 blue dots there, or blue circles, and that number has unlimited significance. In other words, that is an exact number. There's no measure or no guessing, no estimating at all in that one. Okay, so I introduced just quickly then this idea of significant figures. So when I'm counting, these ones have unlimited significant figures. But if I'm measuring something, then there's always a certain number of precision that we have to give. And like I said, it includes the exact one and one estimated one. When you measure anything in science, when you do any calculations with measurements, you always must use sig figs and use them appropriately. You can't give more or less significance or accuracy than what you're given in the question. So it's important that you know how to read how many sig figs there are and then to do operations. Here's some rules then. Rules for significant figures. And say I have this number here, 4.3201. When you look at sig figs, or how many of these, how precise is that number, often in math we say, well, it's 4 decimal places. But in science, I guess sometimes we use decimal places, but typically we use something called sig figs. And it's not 4, in this actual case it's 5. To determine how many sig figs there are really depends on the zeros that you have. Any non-zero number, 1, 2, 3 through 9, all of those ones count all the time. So if you measure something and it's a 1 through 9, that's a significant figure, it counts. Now if you have zeros, it depends on where the zeros are. If the zeros are out front of a number, like this, 0.0032, these zeros out front, this one, and this one, don't count. So any leading zeros don't count, because really they're just holding a place value. I could rewrite that number in scientific notation and those zeros wouldn't even be there. So any leading zeros don't count. Trailing zeros, however, if I go to the time of putting in a trailing zero, then trailing zeros count as long as there's a decimal place. As long as there is a decimal place somewhere in the number. I guess there's always just going to be one, but if there's a decimal place, the trailing zeros, the ones behind, like 4.30, this 0, since it's trailing and since there's a decimal there, this one will count as a significant digit as precision for my number. Any numbers that are within a number, or any zeros that are within a number, like this one here, there's a 0 right there, those ones always count. And like we said on the slide or two before there, exact numbers, if I actually count the numbers, like 1, 2, 3, etc., those ones have unlimited significance. Okay, now when I say unlimited significance, that doesn't mean you have to like keep writing zeros or something behind it, but it just means that this won't be the weakest link when I'm looking at how precise can I be in writing an answer. So let's try some of these. So just I have over here my little hint. So leading ones don't count, trailings count only if there's a decimal, and contained ones always count. All right. So leading zeros, so these ones don't count. So this number here would have 3 sig figs. This one here, I've got a trailing 0. There's a decimal, so this one counts. So this would be 4. Here's another one. I've got, these ones are contained zeros. So contained always counts. So it'd be 1, 2, 3, 4, 5, 6, 7 digits there that are significant. That gives me accuracy. Here I've got some trailing zeros. But there's no decimal place. Therefore, in this number here, there's only one significant digit. The interesting one there, eh? 2,000, only one. However, if I would have written the number like this with a decimal point at the end, then this one, because of that decimal point, would mean that there's 4 significant digits. So careful with those ones. Another trailing 0, no decimal, therefore 2 sig figs. Trailing 0, but there is a decimal, 3 sig figs. I want you to try a couple questions and see how you do. Press pause, come back, we'll reveal the answers. Okay, hopefully you've come back, and hopefully that is what you came up with. Leading, don't count. Trailing, decimal, do count. Contained, count. Trailing, no decimal, don't count. So there's just 2. 1, 2, 3 numbers, there's no zeros at all there. 3. The number 1, 1. Interesting if it's a number 1, is that a counting number or a measurement? I guess without really knowing the context, you wouldn't know. But with the context, you could, if they counted that's unlimited significance. If they measured that and it's about 1, then that significance or that precision would be 1. All right, so let's turn our attention to doing the operations. Turns out that there's 2 different rules for sig figs. One rule is when you're adding and subtracting, and the other rule is when you're multiplying and dividing. If you're adding or subtracting digits, then what it does, or measurements, what you have to go by is the number of decimal places. I've got it there. And it's always the weakest link. So if I were in math, I would add this up, 5, 6, 5, 5. So 55.65, if I was in a math class, the teacher would go, very good, great job. In a chemistry class, the teacher would go, what? That's close. But in your answer, you're giving me more precision than you did in your question. So this answer isn't correct. I'd be docking marks for that. Now, so the rule is you always go to the weakest link. So it's if you're adding and subtracting, you look and see, well, this one has 2 decimal places. This one only has 1. Therefore, in my answer, I can give at most 1 decimal place. So I would take a look here, and I can only give 1 decimal place, so I would round this number here, 55 point, I can only give 1 decimal place. So I look 1 past this, 5 or up, this one gets rounded up to a 7. If this was 4 or less, I'd leave that one at 6. So my answer in chemistry class for this addition would be 55.7. I want you to try a couple. Okay, weakest link, smallest decimal place. Okay, press pause, come back and try it. Okay, let's see how you did on this one. So on the first one, when you add them together, you get 57.667. But here there's 1 decimal place, here there's 3. You got to go to the weakest link, so I can only give 1 decimal place. So that's the only decimal place I can give. Now I need to round. Look at this one, it's 5 or more, this one gets bumped up. So 57.7, and then I don't write any other numbers after that. I don't write zeros. That's not proper to put any number after that. Okay, the next one here, when you had it, this is a sort of funny one. 034 and then 15. But here I've got 3 decimal places. Here I've got 5. I've got to go to the weakest link, so I can only give 3 decimal places. So it would be 0.034. Because this is less than 5, I leave that one where it's at. Okay, so that's adding and subtracting. Weakest link, number of decimal places. If you're multiplying to dividing, well, it's not completely different, but it's different. With multiplying and dividing, there's no decimal places involved. Well, you might have to have them in your answer, but you don't worry about decimal places. In multiplying and dividing, you just worry about how many sig figs each measurement has. So this one here has 3 sig figs. This one here has 2 significant digits. So when you go ahead and multiply those numbers, darn, where's my calculator? Let me grab a calculator quick. There's a calculator. When you use your calculator to multiply that, you're going to round it to the nearest 2 sig figs. All right, 12 days left on my license thing. Okay, here's my fancy calculator. Okay, clear things. So 6.25 times 3.4 equals. So 21.25. So my answer here is 21.25. But here I've got 3 sig figs, here I've got 2, here I've got 4. Can't leave it like that. So this is just sort of a temporary answer. Then I need to write one with only 2 sig figs. So 2 sig figs starting on the left, there's 1, 2, I got to lose the rest of the stuff. So my answer for this one would be 21. Since this is 4 or less, I don't round that one up. So my answer for this question, if I was multiplying that in a chemistry or physics class, physics sometimes use decimal places too, but for sig figs, it'd be 21. In a math class, they would say 21.25, and they would be correct. In chemistry class, 21.25 would be incorrect. 21 would be correct. Okay, why don't you try a couple of those? So just multiply them out, and then round to the nearest sig figs, and then press play. Okay, let's see what you got. This is sort of what I did. When you multiply those, you get this answer. This is 2 sig figs, there's 5, so I got to round to 2. So here's a 68, that one's 1 more, so I bounce that one up to a 9. So my answer, correct answer for that would be 69. Multiply these, I got 4 sig figs. Here I've got 3, so at most I can give 3 digits of precision. So 1, 2, 3, since this is less than 5, I leave that one alone, 63.9. 3 sig figs, 4 sig figs. Here's my answer. I need to go to 3 sig figs, 1, 2, 3, less than 4, I leave that one alone. So those are my answers. Okay, maybe just last thing for this video is to look at rounding rules. Make sure that you practice these a little bit. I just threw out some numbers with how many sig figs I wanted you to round them by. And maybe try them if you want. Press pause and then come back and see if you got them right. Round this to 3 sig figs. 1, 2, 3. This one's more than 5. I have to bounce that one up. 2.36. This one. 2 sig figs. So 0.00. Leading zeros don't count. 2 sig figs. So 3, 4. This is a 5, so this one has to get bumped up to a 35. Notice I don't write anything else after that. 3 sig figs. Okay, 1, 2, 3. 1, 2, 3. This one is less than 5, so I don't round that one up, but, well, hold on here now. What do I do there? Because this is 1,000 something, right? If I just left 123, that wouldn't be right. So maybe I've got to put something in there. How about if I put a 0 in there? Is that 0 significant now? It's not, right? A trailing 0 without a decimal doesn't count. So 1230 would be the appropriate way to round that one right there. There's another one. 3 sig figs. There's 3. There's a 3 there, less than 5. Leave that one alone. So it'd be 150. But if I just put 150, that's only 2 sig figs. So I need to put a dot at the end, a decimal. Now I've got 3 sig figs. 2 sig figs. Here's my 2 right there. More than 5. This one gets bounced up to a 58. There's 2 sig figs. And last, 3 sig figs, 100. This one's less than 5, so this one stays. So this would be 100. Oh, another trick one, right? If it's 100, if I don't put a decimal, that's only 1 sig fig. So I have to put a decimal there to indicate that that's 3 sig figs. All right, in this section then we've looked at precision, and we've looked at the importance of precision in science. And we've seen that significant figures, that's what we call the precision. And we've also looked at using the 4 main operations and the rules that go along with maintaining the proper amount of precision.